get rid of that. Okay, so today we're looking at rational functions. And it's rational functions that have asymptotes. And a rational function is a function that has a numerator, it's some function, and a denominator. And I like to use n of x and d of x because n stands for numerator and d stands for denominator. And in the example that we just did, you had a numerator and you had a denominator, and it resulted in a function with an asymptote. So let's talk first about the vertical asymptotes. Vertical asymptotes are going to occur whenever you have x values where the function is undefined. Okay, so the function doesn't exist there. And to find those vertical asymptotes with a rational function, we're going to set our denominator equal to 0 and solve for x, and then name the vertical asymptotes as the equation of a vertical line, like x equals a. So I want you to take a moment and let's graph this first function, f of x equals 2x plus 1 over x plus 3. And please remember, we have to put parentheses around the numerator. We have to put parentheses around the denominator. And now we can create that graph. So enter that in your y equals screen. And for this function, it's sufficient to just use a standard viewing window. That will be absolutely fine. So when I use my standard viewing window, I'm getting a graph that looks like this, and I hope you are as well. Looks like we have a vertical asymptote at -3. Now, the closer you get to -3 from the left, in fact, let's explore this for a moment. If you can, let's go back to your table. So do second table. And choose a number like, let's say -4. If we choose -4, you get y equals 7. And now let's choose a number that's closer to -3, like maybe -3.5. And you get a little bigger number. And how about like -3.1, you should get a bigger number, and -3.01, and you get now enormous, and you get bigger and bigger numbers. You guys following that? So the closer we look at x values as we come towards -3 from the left, we're getting higher and higher y coordinates, and you could continue to choose closer and closer values. You could choose -3.00001 or -3.0000001. I mean, it doesn't matter. The closer you get to -3, those y coordinates are going to continue to increase, but they're never gonna, you're never going to be able to choose -3. If you choose -3, what do you get for a y coordinate? You get an error, okay? And why do we get an error? Look at the equation. Who knows why we get an error? Go ahead. Awesome, yeah. When you get -3, the denominator is 0. That makes the fraction undefined, okay? So we're going to always get vertical asymptotes wherever we have the denominator equal to 0. All right, let's look at a different case. I'm going to scoot over to this third problem. And I want to write this in factored form. I'm going to write this as x plus 2 divided by, in the denominator, this factors to x plus 2 times x plus 5. And looking at that, before you even graph it, where do you think the vertical asymptote or asymptotes will be? What do you think? Okay, so we're thinking there's going to be asymptotes at -2 and -5. So let's graph that. And when you do, please put an extra set of parentheses around this denominator. Okay? Make sure you have that extra set of parentheses so we're dividing by that entire denominator. So everybody getting the correct graph? You didn't. What's the matter? Oh, you've got your parentheses around the denominator.
Nope.
Extra set of parentheses here.
Oh,
Yeah, need an extra set of parentheses. Okay, so I'm wondering if I did something wrong here. I'm only getting an asymptote at -5. Does anyone else have the same graph? Okay, so what do you think we're doing wrong, or why are we getting this? What do you think, Mark? Awesome. I'm so glad you either remembered that or figured that out. So the x plus 2's in this function, they both divide out. So the graph of this original equation is identical to the graph of f of x equals 1 over x plus 5. But there's one point where it's different. Do you know what that point is? Our original function, well, let's trace to -2. Just trace to -2 and see what you get. Trace to -2, you don't get anything. You get y equals nothing, right? So that means the original function was undefined at x equals -2. So on your graph, if you arrowed to your, trace along your graph and get closer and closer to -2, you get values, but as soon as you get to -2, it doesn't exist. So there's actually a hole in the graph there, and we're going to indicate that by actually putting a little hole on our graph. So vertical asymptotes arise whenever you have the denominator equaling 0, so at x equals -5. But if these factors divide out, like in this example, the x plus 2's divide out, you're just going to get a hole in the graph. So this results in a hole. This results in a vertical asymptote. I'll just abbreviate that VA. Okay, so that's an introduction to vertical asymptotes. So let's move on now to horizontal asymptotes. That'll be our next thing. So I'm going to clear this for a second and we'll scroll up. Let's talk about horizontal asymptotes. The rules for horizontal asymptotes have to do with x approaching positive infinity or x approaching negative infinity. And I want to look at a few functions, and we're going to sort of divide and conquer because we only have about 10 minutes left. So I need you guys right here in this section of the room. You're going to graph this function right here. And then let's have, in the middle section of the room, you all graph this problem right here. And then let's have you all graph this problem right here. And we're going to take a look at those graphs and talk about the horizontal asymptote. So as you create your graph, see if you can figure out the horizontal asymptotes. Remember, you're putting your numerator and your denominator in parentheses. That's the only way you're going to get a correct graph. Numerator in parentheses divided by a denominator in parentheses. You guys come up with a graph? Okay, so that's your graph. What did you get? Okay, you have the numerator divided by the denominator. The numerator and the denominator are both in parentheses. It's like the hard one.
Wait, oh my goodness.
Okay.
I got my graph.
Yeah, it's kind of small.
Let's go with 1 and 1.
first graph looks like this. We have this image, it goes down, it drops down, it goes a little higher. Somebody said it looks like a heartbeat. Kind of does. It's like a heart rate monitor a little bit. Okay, so talk to me from this group. What do you think is the horizontal asymptote? What's the graph approaching as x gets large or x gets small?
0.
Okay, looks like y equals 0, and I'm going to agree with you. Y equals 0. Okay, middle group. What does your graph look like? Everybody come up with the same thing? Okay, you got that. Okay, good. Can you see a horizontal asymptote? Can you see a value that it's approaching? Can I borrow your screen for a minute? What does it look like it's approaching, guys? Okay, if I want to know what this is approaching, I'm asking you the question, what are the y coordinates getting close to as x gets infinitely large? So go to your table of values and type in a bunch of huge numbers for x. Type in x equals 100 and x equals 500 and tell me what value are the y coordinates approaching? What do you get? You got 5, you got 5, 5, okay? So sounds like y equals 5 here. Okay, and lastly, this crew over here, do you guys all sort of agree on a graph? Okay, so it looks something like that. Does your graph look something like that too? Awesome, okay. So it looks like for this equation, our graph looks something like this. It's coming down here and scooting up. And then it's doing this. Okay, tell me, is there a horizontal asymptote? Is there a value horizontally that it's sort of approaching? Doesn't look like it. Looks like as x becomes increasingly negative, we're increasing, in this direction. So if we go to the left, really, really small negative values, the function is still increasing. And as we look at very large values of x in this direction, the function is really, really increasing. Okay, so we say there are no horizontal asymptotes in this case. Okay, the function just keeps increasing without bound if we go to the left or the right. So let's look at our 3 cases, and I'm wondering if any of you remember this from Algebra 2. So stop whatever you're doing right now, put your calculators down on your desk, upside down, so you're not tempted to mess around anymore for a minute. Here are our three situations. When the degree of the numerator is less than the degree of the denominator, so it says the horizontal asymptote is y equals 0. Here's an example. The degree of the numerator is what here? 2. Here the degree of the denominator is 4. So the degree of the numerator is less than the degree of the denominator, so our horizontal asymptote is always going to be y equals 0. And if you think about it, perhaps it makes sense, because if the numerator is getting large, sort of at an x squared rate, and the denominator is increasing at an x to the 4th rate, the denominator is increasing much, much faster than the numerator. And so anytime you have a fraction where you're increasing the denominator, like 1/2, 1/3, 1/4, 1/5, 1/100th, 1/1000, that fraction is essentially approaching 0, and it will always approach 0. The next case is when the degree of the numerator is equal to the degree of the denominator. So that's going to be which case? Left, right, or middle? It's the middle. The degree of the numerator here is 2, the degree of the denominator is 2. They said y equals 5 is the horizontal asymptote. Look at the ratio of the coefficients. You have 5 over 1. Okay, and it will always work that way, whatever is the ratio of the coefficients, because essentially, if you have a function increasing at a rate of x squared in the numerator, and a function increasing at the rate of x squared in the denominator, 5 times that rate in the numerator over 1 times that rate in the denominator means that the fraction will eventually level off to just 5. Mark?
So you just divide them?
You just look at the ratio, 5 over 1, so it's just 5. if this was in the numerator, let's say it was 2x squared and the denominator was 3x squared, 2 over 3. That would be your horizontal asymptote, 2/3. Yeah. Raise your hand if you've heard this before. For some of you, it's review. For some of it, it's brand new. Okay, depends on what your Algebra 2 experience was. Okay, and then the last one, when the degree of the numerator is greater than the degree of the denominator. So now we're looking at degree 3 over degree 1. In this case, greater degree in the numerator, less degree in the denominator. In that case, your numerator is increasing really, really fast at a rate of x cubed. Your denominator is increasing only at a rate of x. So those numbers are going to keep getting larger and larger. No matter how big x gets, the function just goes off to infinity, so there is no horizontal asymptote. Okay? So you're going to use those 3 rules. You can come back to this tonight in the notes. You know, it's on my website, and I'm going to post this video as well. You can come back and review this part of the lecture if you need a little help. Okay, as we finish up, let's do one more thing. I want to just look at some examples quickly and talk about horizontal and vertical asymptotes based on the rules that we just discussed. So the first example, if we were talking about the vertical asymptotes, remember we're looking at where is the denominator 0. So we want to take this f of x function and let's write it in factored form, x plus 1 times x minus 1. And now, Mark, this was the case that you described earlier. What's happening in this case that's kind of unique? The x plus 1's divide out. So this factor, x equals -1, that results in a hole in the graph. Whenever the factors divide out, that's when you get a hole. Whatever factors are left over, that's where you get a vertical asymptote. So we have a vertical asymptote at x equals 1. Now, we're going to apply those 3 rules when we're looking for the horizontal asymptote. So the degree of the numerator is 1. The degree of the denominator is 2. When the degree of the numerator is less than the degree of the denominator, what's our horizontal asymptote? 0. Y equals 0. Okay, it's exactly by those rules. So we have a horizontal asymptote at y equals 0. And just thinking about it in terms of the rates. The numerator is increasing at a rate of x. The denominator is increasing at a rate of x squared. It's increasing faster. So the fraction has to approach 0. All right, next problem. With this one, when we set the denominator equal to 0, we have 4x minus 6 equals 0. That is 4x equals 6, or x equals 6/4, which is 3/2. That tells us our vertical asymptote. Okay? So we have a vertical asymptote at x equals -3/2. Oops, excuse me, positive 3/2. Somebody tell me about the horizontal asymptote. It's 1/2. How did you get 1/2? 2 divided by 4. Okay? The degree of the numerator is the same as the degree of the denominator. They're both increasing at the same rate. So your horizontal asymptote is 2 over 4, or 1/2. Okay, one more quickly. What's your vertical asymptote here? X equals -1. Vertical asymptote, x equals -1. And your horizontal asymptote is none. All right, now listen carefully about homework, guys. You have some problems in the book. You're working on your study island, and I have an SAT review packet because a bunch of you are taking the PSAT coming up, and a bunch of you still are taking your SAT. Okay? So this review packet is due on Thursday, and I need someone to collect the papers for me today. Noelle, can you collect the papers? Guys, Noelle is our new class captain. She's going to run around and collect papers. Let's hear for Noelle. What I want to buy is, what else do you guys sell? Candles? I might buy candles. candle. Oh, candle. Okay, all right. Say what? You promise. You share your promise. I will. I'll buy a candle. First your kid gets you first. I'll buy a candle.
Yeah.
I already got you.